So we just talked about finding the area underneath the graph of a function. And what this really amounted to doing is adding up the area of a bunch of rectangles. So for instance, if we have our function f of x, and we'll assume it's continuous, on a closed interval ab, well, first we partition ab as follows. So we just pick points. So we'll let a be x0, and then we have x1, x2, all the way up to xn, which we'll let be b. Okay, and so delta x is b minus a over n, which is just the difference between two of these points in my partition, like that. Okay, so anyways, we talked about this. We partition the interval, and then let's just say we want to use the right endpoint. Then we have the approximation to the area under the curve of f of x on this closed interval a to b is just what? Well, it's delta x times f of x1 plus delta x times f of x2 plus all the way up to delta x times f of xn. And this is just base times height, base times height, base times height. And for the height, we're just using the right endpoint, evaluating the function. That gives us the height of the rectangle. So there's a way that we can actually suppress this sort of long sum. So just, we're adding up a bunch of numbers here. We can write it in kind of a compact way. So we can say that this is equal to this. Now this fancy symbol here is the Greek letter sigma. Okay, so this is called sigma because we're using the Greek letter sigma notation. Okay, and well, what it means is this. But instead of writing out all of the terms of the sum, we're just putting a single kind of summation right here and then indexing it with this letter I. Okay, so just some pieces of terminology. Like we said, this symbol is the Greek letter sigma. Okay, it's kind of like S in English. I is called the summation index, or in other words, the index of summation, sometimes just called the summation index, or the summation variable, whatever you want to call it. Okay, so it's just the variable that's indexing the terms in the sum. So 1 in this case is the lower limit of summation, or the lower summation limit. Okay, so that just means we're starting at I equals 1. Okay, so this is the I equals 1 term. I equals 1, I equals 2, and this is, of course, the I equals n term. So each term is just indexed by I. 1 is the lower summation index, and then n will be the upper summation limit. Okay, so there's some just simple notation. And now the advantage of sigma notation is it allows you to express very simply the sum of a lot of numbers. Okay, and that's exactly what we're doing when we're finding the area under a curve. We're having to add up the area of a lot of small little rectangles, and so sigma notation allows us to do that in a very compact way. And so our next goal is to develop formulas for common sums. So there are some special functions that come up with regards to this index of summation I that we want to just sort of be able to say, well, this is what it is. Okay, and you'll see what I mean in a second. But before we do that, let's actually just see a couple of examples. Okay, so let's look at some sigma notation examples, just to kind of get a feel, if this is the first time you're seeing this, what's going on, and to sort of convince you that there's really nothing crazy. It's just a kind of a compact way to write things that might be difficult to write otherwise. So for instance, if I wanted to add 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 plus 10 plus 11, okay, that's probably enough to get the point across. Well, I can write this in the compact form, sum, okay, and I need an index of summation, so I'll let that be I. I could also use k, and so maybe here I'll use k because it really doesn't matter. But now I'm increasing 1, so the sum end, each term that I'm summing, is increasing by 1, so I'll actually just let the sum end be k. And I'm starting at 1, so that's my lower limit, and I'm ending at 11, so that's my upper limit. So I can write this sum as the sum k equals 1 to 11. Now also, we don't have to start at 1. So for instance, if I have j equals 3 to 7 of j squared plus 1, okay, so what does this mean? Well, all I'm going to do is I'm just going to take whatever the lower limit is for j, which is 3, and plug that in. So this should be 3 squared plus 1. This is the j equals 3 term. And then I go to the j equals 4 term. That's going to be 4 squared plus 1. So this is j equals 4. And then I just keep going. 5 squared plus 1. This is the j equals 5 term. 6 squared plus 1. J equals 6 term. And so how do I know when to stop? Well, I stop exactly at the upper limit. So that'll be 7. 7 squared plus 1. Okay, and of course, in a specific example like this, I can actually just write what the sum is equal to. I can just perform the sum, and I see that actually this is equal to 140. So these are just some examples of how sigma notation works. So hopefully you get the idea. Because next, we actually want to try to develop some formulas for general sums that will come up. Okay, so let's start with something pretty simple. Let's say that a is a constant. Okay, so if I add a n times, I can write that in sigma notation. So I can do I equals 1 to n of a. And so now notice that because my sum end here is a constant, it acts just like a constant function. This is really nothing more than just a plus a plus a plus all the way to a. And then how many a's do I have? Well, I have 1, 2, 3, 4, 5, 6, all the way up to n a's. So I can actually write this even simpler. This is really just n times a. That's how multiplication is defined, or at least a very primitive way to define multiplication, as repeated addition. When we have repeated addition, it really is just multiplication. Okay, so that's a really simple sum formula written in sigma notation. So if we have a sum and we have a constant in the sum, then we just get that constant however many terms are indexed by the sum. So let's try one that's a little bit more interesting. Let's look back at this example. But now here, I'm going to start at 1 and then just add all the way up to some number n that's unspecified. Okay, so this is the sort of thing that happens when we're looking at areas under a curve. We just want to break up something into n pieces where n is an arbitrary number. And then maybe later we want to take that, the limit as n goes to infinity, or something like that. So just to remind you, this is really 1 plus 2 plus 3 plus 4 plus, keep going, and then we'll have n minus 3 plus n minus 2 plus n minus 1 plus n. Okay, and of course I'm skipping, if n were 100, I'm skipping kind of the middle terms, but this is the idea. You just increase 1 every time until you get all the way to n. Now the trick is here to really just apply the associative property and the commutative property of addition. So I'm adding up this finite collection of numbers. The associative property basically says I can add them up in any order I want, okay? So here's what I'm going to do. I'm going to pair 1 with n, 2 with n minus 1, 3 with n minus 2, 4 with n plus 3, and so on. Okay, so what are we going to have? Well, we're going to have 1 plus n, okay, that's just 1 plus n, and then 2 plus n minus 1, okay, so I just pair those terms, add those terms together first, then 3 plus n minus 2 plus 4 plus n minus 3 and so on. And notice what happens here. What are these sort of paired up sums? So this is just n plus 1. Okay. This is n minus 1 plus 2. That's also just n plus 1. Okay. And then plus, well, hopefully you see the pattern. all of these terms, the way I've paired them up, are going to give me n plus 1. So I can actually apply this first formula. I'm just adding up the same number so many times. But now the question is, how many times have I added n plus 1 to itself? Well, I paired them up one by one, so it should be n over 2, right? So I took half of the numbers and paired them with half of the other numbers. So what this should be is n over 2 times n plus 1, or n times n plus 1 over 2. Okay, so this is an example, like I said, of another sum formula written in sigma notation. If I just sum n terms, where each term just starts at 1 and goes all the way up to n, then the answer is n times n plus 1 over 2. So let's look at a few examples just to get the hang of this. Okay, so let's say we wanted to look at k equals 1 to 10 of k. So this is 1 plus 2 plus 3 plus 4 plus all the way up to 10. And now we could do this in a calculator, or maybe even in our head. We could just say 1 and 2 is 3, and then 3 is 6, 4 is 10, 5 is 15, add 6 is 21, etc. But what this formula we just found says is that actually I just take 10 times 10 plus 1 over 2. And what do I get? Well, 55. See how quick that is? And maybe, 10 isn't really that big of a number, but what if I wanted to add all of the numbers up to 100? Now, even if you use a calculator, this is going to take a while. But look how fast it is with this formula. This should just be 100 times 100 plus 1 divided by 2. Or in other words, 50 times 101. But what is that? Well, 50 times 101, that's just going to be 50 hundreds plus 50, so 5, 0, 5, 0. Okay, so that's kind of the hang of it. That's how it goes. We have this nice formula for adding up a bunch of numbers, and we can use it to add up numbers really quickly. And this is going to be super helpful when we try to find areas under a curve. Alrighty, so here we want to show another summation formula in sigma notation. So if we add up the numbers 1 to n and square them, so instead of just adding them 1, 2, 3, 4, 5, we add up their squares, so 1 plus 4 plus 9 plus 16 plus 25, etc., then we get this, n times n plus 1 times 2n plus 1 over 6. And I'll say that this is a challenging problem. Okay, so this is not for the faint-hearted. And there are actually a lot of different ways to do this, but there's one way that I think is maybe the most elementary. So you can do this by mathematical induction, which is probably beyond the scope of this class. Of course, if you've seen that before, then I'm sure you can do this. It's a pretty simple exercise in that. However, I'm going to do it slightly differently. And I'm going to start by writing something extremely unrelated. Okay, but this will illustrate the sort of tricks you can use when trying to evaluate sums. So I'm going to look at n plus 1 cubed minus 1. Okay, so this seemingly has absolutely nothing to do with anything. Okay, but watch this. This is certainly the same thing as n plus 1 cubed plus n cubed minus n cubed. Okay, so this is just 0, right? I'm just adding 0. So this is just 0. Of course, this is a very useful trick in mathematics to add 0 creatively. And then we have n minus 1 cubed minus n minus 1 cubed. Okay, that's also just 0. And then we keep going all the way to 2 cubed minus 2 cubed plus, minus 1. And again, this is just 0. So I just added in 0 a bunch of times, but this is still a true statement. Okay? And so the reason I want to do this is I'm trying to actually write this in what's called a telescoping series, or a telescoping sum. Okay, so now what I'm going to do is I'm going to reassociate. So I'm going to take this n plus 1 cubed and subtract n cubed. So this is n plus 1 cubed minus n cubed, and then plus n cubed minus n minus 1 cubed, and then a bunch more terms. And then the last term, I can take this 2 cubed and subtract 1, but I can just write 1 is 1 cubed. Okay? So again, I just reassociated the terms in the sum like this. And now I'm going to write this in sigma notation. So this is the sum. Let's see, so we're starting at I equals 1 and going all the way to n. And then what are we adding up? We're adding up I plus 1 cubed minus I cubed. Okay, so nothing strange here. But now what I want to do is actually expand I plus 1 cubed. So remember, I plus 1 cubed is just I cubed plus 3i squared plus 3i plus 1. But if I subtract I cubed, this is the sum from I equals 1 to n of 3i squared plus 3i plus 1. Okay? But now I'm going to use basically the distributive property. So all of these terms are being multiplied by 3, all of these terms are being multiplied by 3. So I can write this as 3 times the sum I equals 1 to n of I squared, and notice this is actually the sum I'm looking for, right here. Okay, and then what's left? We have plus 3 times the sum I equals 1 to n of just I, and we actually know what that sum is, and then this sum I equals 1 to n of just 1. Okay, so technically I've used the distributive property to factor out this 3, and then the associative property I've just added up, instead of adding this term plus this term, I'm just adding up just these terms and just these terms and just these terms. And so what we get here is 3 times, let's call this sum we're looking for s. So 3 times s, so this thing is s right here. Because that is what we're looking for, like I said. And then the next term is plus 3. And then the sum I equals 1 to n of I is just n times n plus 1 all over 2. And then plus, if I add I equals 1 to n of just 1, well, that's just 1 plus 1 plus 1 plus 1 n times. That's just going to be n. Alrighty, so we're almost there. So now if I just solve algebraically for s, so remember that all of this is equal to n plus 1 cubed minus 1, we should get that s is equal to, well, n plus 1 cubed minus 1 minus, so I'm just going to subtract these other terms over, 3 times n plus 1 over 2 minus n, and then I need to divide by 3, all over 3. Okay, good. So what is this? Well, you just do a little bit of, what is this? It's just algebra. Okay. And rest assured that you do indeed get n times n plus 1 times 2n plus 1 all over 6, as we should. So again, like I said, this is a very difficult problem. I would not expect anyone who's seeing this for the first time to be able to do this, but I think it's a very good example to see because it illustrates all the different tricks and techniques, or at least some of them, that you can do with sigma notation. So we're looking for this sum. We kind of look at this unrelated sum and force it to be what's called, of course, this telescoping sum. And then we just do a little manipulation and we get what we want. So it's just a really, not, especially if you're interested in math and interested in kind of moving on in math to more advanced math, this is, illustrates a lot of very nice ideas that you'll see again in the future if you continue on. All right, so we have another sum that we want to show. We want to show that, again, now if we add up the numbers 1 to n but cube all of them, we get this formula. But the interesting thing to notice here is that n squared times n plus 1 squared over 4 is actually just the sum from 1 up to n of just I, that quantity squared. And now I promise you that if you're seeing this for the first time, this is completely going over your head. But I just want to say that if you haven't seen this before, in my opinion, this is one of the most beautiful formulas in mathematics. It is absolutely just amazing. There's really not, we'll show why it's true, but there's really not kind of a deep reason of why it should be true. It's very coincidental. Now, there are ways to kind of think about why it should be true, but it's just very coincidental, and it's one of those things that when you fully start to understand, you can't help but just marvel at the beauty. It's one of those things that's just, it's almost a work of art, if you will, this statement as it is. Okay, so that's my cell on this formula that is beautiful. Now let's actually see how to justify it. And the way we're going to justify it is we're actually going to start with the right-hand side over here. Okay, and we're going to just expand this, this is a sum of terms times another sum of terms, and we're just going to kind of use it's not foiling, but it's basically just the distributive property. We're going to distribute out all of the terms and just see what happens. Okay, so the sum I equals 1 to n of I squared, and I'm going to write it out actually out of sigma notation so I can really show you what's going on. Okay, so 1 plus 2 plus 3 plus, okay. So we're just squaring this, which, because each one of these things is equal to n times n plus 1 over 2, their product will be n squared times n plus 1 squared over 4. And now what do we get? Well, notice that we're going to have to take 1 and multiply it by all these terms, and we're going to have to take 2 and multiply it by all these terms. But there are sort of diagonal terms. So 1 is going to get multiplied by 1, 2 is going to get multiplied by 2, 3 is going to get multiplied by 3, and of course all the other terms too, but I want to isolate those terms. So I'm going to have 1 squared plus 2 squared plus 3 squared plus all the way to n squared. So of course n is going to be multiplied by n for one of those terms in the distribution. And then what are we left with? What else are we adding? Well, we have all the cross terms. So 1 being multiplied by 2, 1 being multiplied by 3, etc. Okay, and so we can write this actually in sigma notation. So we're going to get 2 times, and the reason we're going to get 2 times is because think about if I multiply 1 by 2, I'm also going to be multiplying 2 by 1. So I'm getting doubles of the same terms. And what are those terms? Well, I add, okay, I equals 2 to n of I, and then we add j equals 1 to n minus 1, sorry, to I minus 1, of j. Okay, so what in the world is going on here? Well, all I'm saying is if I fix, let's say I equals 2. Okay, so I start with I equals 2. What am I going to do? Well, I'm going to multiply 2 by everything less than 2. So in this case, just 1. So I'm summing from j equals 1, in this case, to 1. So I'm taking 2 and just multiplying it by 1. Then when I go to I equals 3, I'm multiplying 3 by 1 and 2. And then when I go to 4, I'm multiplying by 1 and 2 and 3. And then I also have the symmetric case, 2 by 1, 3 by 1 and 2. Okay, but that's where this 2 is coming from, because I'm really getting the same terms twice. Alrighty, so this is a mess, I understand, but this is how the proof goes. Okay, this is, or at least one of the simplest proofs. So first of all, notice that we have a formula for this, 1 squared plus 2 squared plus 3 squared all the way up. But I'm actually not going to write the formula. I'm just going to write this as the sum I equals 1 to n of I squared. And now here, the sum from j equals 1 to I minus 1 of j gives, well, it's going to give I minus 1 times I minus 1 plus 1, which is I, over 2. Okay. And then, of course, we're multiplying this by I, so this is times another I. So the 2's will cancel, and what are we left with? Well, we're left with the sum I equals 1 to n, sorry, 2 to n, 2 to n, these 2's will cancel, like I said. And this is just going to be I cubed, so I times I times I, and then minus I times I, so I squared. Okay, and then we also have this other term, so plus sum I equals 1 to n of I squared. Okay, so we're almost home. This is what we need to do. So you notice that actually this is the sum I equals 1 to n, or 2 to n, of negative I squared, and this is positive I squared. So we have I equals 2 to n of I cubed, which is almost what we want over here, notice. And then minus I equals 2 to n of I squared plus sum I equals 1 to n of I squared. Every single one of these terms is going to cancel except the I equals 1 term here. So we're just going to be left with plus 1. But we can actually write this as I equals 2 to n of I cubed plus 1, but 1 is really the same thing as 1 cubed. So this is really equal to, we can just put the 1 cubed in this sum, I equals 1 to n of I cubed. Okay, so we started with the right-hand side, we ended with the left-hand side by equivalent statements, equality all the way through. So we're done. Okay, and now maybe more importantly than the justification, that was a little bit technical, I agree, I want to show you a couple of examples. So maybe you can start to see kind of why I say this is such a beautiful formula. Okay, so let's just look at a few examples. So if n is 1, what this is saying is that 1 cubed equals 1 squared. Okay, well that is not very remarkable. There's nothing really interesting there. But let's look at the n equals 2 case. So the left-hand side is saying 1 cubed plus 2 cubed equals 1 plus 2 all squared. Okay, is that true? Well, 1 cubed is 1, 2 cubed is 8. So here we have 9, 1 plus 8. And then this is 1 plus 2, 3. 3 squared is 9. Okay, so a little bit more interesting. You see, if I just say 1 cubed plus 2 cubed, that's the same thing as saying 1 plus 2 and then squaring it. Okay, so maybe that's just coincidental, let's look at n equals 3. What the n equals 3 case is saying is that 1 cubed plus 2 cubed plus 3 cubed is the same thing as 1 plus 2 plus 3 all squared. And hopefully you're starting to see how unexpected this is. There's really no reason why cubing these numbers and adding them together is the same thing as adding them together and then squaring them. Those are very different procedures. But look, 1 cubed is 1, 2 cubed is 8, 3 cubed is 27, 1 plus 8 plus 27 is 36. Look at this, 1 plus 2 plus 3 is 6, 6 squared is 36. And now, the amazing thing, I mean, you probably completely zoned out while I was justifying this to you, but we just proved that this remarkable pattern always holds. So if I take 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed all the way up to 100 cubed, that will be the same thing as adding 1 plus 2 plus 3 plus 4 all the way up to 100 and then squaring it. It's truly remarkable. And if you're interested, I encourage you to actually go and look. There are examples of art that tries to illustrate this concept. And even though there are some amazing pieces of art, this is a tough thing to visualize. It really is. I have spent probably more time than I needed to just trying to wrap my head around this, very beautiful identity. And I hope, at least with these first few examples, maybe you can go and try to do more. You're starting to understand that this sort of very simple number theoretic statement is why people say math is so beautiful. I mean, this kind of phenomenon just nags at you, and you're like, why should this be the case? But it is, and it's so simple to express. So again, just maybe a selling point if you're interested in looking into maybe some deeper pure math ideas, this is a good starting point. All right, so now that we've proved these very interesting summation formulas using sigma notation, let's see how much mileage we can get out of them. So notice that this sum from k equals 1 to 36 of k times k minus 1, of course, what we're really looking at here is this. So this is 36 times 35 plus 35 times 34 plus all the way 3 times 2 plus 2 times 1. Yeah, and so, I mean, you could sit there with the calculator and do it, but let's just use the formulas that we know. So, first of all, notice that this is the sum. K equals 1 to 36. We can actually manipulate the summand. This is going to be k squared minus k. Okay, and now we can use the associative property, so we can just add all the k squareds and then subtract adding all the k's. Addition is great in that regard. It has all these nice properties, so we might as well use them. So this is 1 to 36 of k. And now we have formulas for both of these. This should be, well, 36 times, 36 plus 1 times 2 times 36 plus 1 all over 6 minus, this guy is going to be 36 times 36 plus 1 all over 2. Okay, in this case, n is just 36. But now this is much simpler to plug into a calculator. Okay, instead of doing, something like 36, maybe even more than that, operations, now we're just doing a handful. And so what do we get if we plug this in? Well, we get 15,540. So just like that, plug it in a calculator, we are done. That's what this sum is equal to. Okay, same old song and dance here. So, let's just think about what this is asking. Well, it's asking to find the following sum. So 3 times, we got to add 1 to m, so 6 cubed plus 3 times 7 cubed plus all the way to 3 times 51 cubed. Okay, so again, don't plug that in your calculator. It's going to take, well, it's not going to take literally forever, but it's going to take a while. What we really want to do is use our sum formulas. But now notice that we have a problem. Our sum formulas apply when the sum starts at 1. And so what do we do when the sum doesn't start at 1? Well, we do the following. So first of all, the fact that I'm shifting the index m plus 1, m, notice that I'm really starting at 6 and ending at 51 of just cubing those numbers. So what I mean is that this is the same thing, is starting with my lower limit at 6 and going to 51 of 3 times m cubed. Okay, so take a second, make sure you believe that. So, just think about this. The first number I'm cubing is 6, then I'm cubing 7, right, 6 plus 1. And the last number I'm cubing is 51, because here I have 50, but I'm adding 1 to it before I cube it. Okay, so that's sometimes called re-indexing a sum, which is another really common trick with working with sigma notation. And so, well, certainly I can just factor out this 3. That's just factoring using the distributive property. So m equals 6 to 51 of m cubed. And so, like I said, I'm almost done, except I really only know the formula if m starts at 1. Well, let's just make it start at 1. So this is 3 times, well, the sum from 1 to 51 of m cubed. But now I really don't have the m equals 1, m equals 2, m equals 3, m equals 4, m equals 5 terms in this sum, so let me just subtract them. And there we go. So that's the trick. If you don't start at 1, we'll just make this sum start at 1 and then subtract off the terms that you're not interested in. Okay, so what is this? This is 3 times, well, let's see, 51 times 51 plus 2 over 2. That quantity squared. So remember, adding up the cubes is like adding up the numbers and then squaring that value. That really cool fact that we knew. And then minus, well, similar thing. This is just going to be 51 times, I made a mistake here. This should be 51 plus 1. There we go. And that's squared. And this will be 51 not 51, sorry. There. Okay, so this is correct. And now for this sum that we're subtracting off, we're ending at 5. So this should be 5 times 5 plus 1 over 2 all squared. There we go. Okay, so make sure that looks right to you. That looks right to me. Okay, and then what do we get? Well, we get 5, 2, 7, 4, 1, 5, 3. So that is a big number. The sum is very large. But look how relatively easy it was to get this sum by using these summation formulas. Okay. So as we'll see, we're now going to apply these summation formulas that we know in sigma notation to help us evaluate or find the area underneath curves. And they're going to be very useful.